Yeah, I'm terrified of soda and all that stuff that could lead to that. It's one of my fears is kidney stones.
I'm not winning any awards for the best wife ever, because I'm like, suck it up. Yeah, it hurts, whatever.
Feel scared.
So all of you guys are married?
I'm not married.
Oh, okay. I'm in the same league with you.
Maybe someday.
I cannot manage.
I'm married and have 3 teenagers, so I've got. His doctor was basically trying to convince me that I was being kind of really mean. We have to go back to the ER again. Yeah, it hurts, okay?
As long as it's taken care of, no one's required to be enthusiastic about the whole situation.
Okay, let's start from this section. It's called column space and the null space of a matrix. It's not very hard. So let's start from the column space section. Theory definition 2.1. So the column space of an M by N matrix A, which we always write as written as call A, is the subspace of Rm, is a subspace of Rm spanned by the columns of matrix A, spanned by the columns of the matrix A. Now, if A equals to, this is A1, the vector, A2, all the way to, let's say, AN, then the column of A equals to the span of A1, A2, all the way to AN, whereby this is the same as A1X1. Actually, this is equals to, we usually start from X1, A1 plus Xn, AN, whereby X1, X2, all the way to Xn are elements of real number. And this is the same as AX, where X is elements of Rn. The same as that. So the column space A are actually the subspace of Rn, which are spanned by the columns of A. Now, how can we determine whether it is a column space? Let's take an example of example 4. Determine whether B is in column space of A, where A is equals to -3, -2, 0, 0, 2, -6, 6, 3, and 3, and B equals to 1, 14, and -9. So determine whether B is in the column space of A. This is actually similar to what you were doing last time. So we need to determine whether B spans A. And to check that, then what you need to do is we just need to check whether A and B, that matrix there, is what? Is consistent. So we just want to check whether that is consistent. Then, so this is -3, -2, 0, 0, 2, -6, and then 6, 3, 3, and then 1, 14, and -9. So when we reduce this to echelon form, reduce to echelon form, then what we get is -3, -2, 0, 1, 0, 1, -3, and 7, and 0, 0, 0, and 0. So that is what we get. So basically, since the last row, since third row is not contradictory, then AX equals to B is consistent. And B is in the column space of A. B is in the column space of A. Okay, what about the null space? So what about the null space? Let's look at definition 2.2. So the column space is the subspace of Rm, the subspace of Rm. But the null space will be the subspace of Rn. Will actually be the subspace of Rn. So definition, so the null space of an M by N matrix A written null of A is the set of all solutions of the homogeneous matrix equation. Equation AX equals to 0. It is actually the solution of the matrix equation, homogeneous matrix equation. We said homogeneous is where AX equals what? AX equals to 0. AX equals to 0. i.e., the null space of A is equals to X, which is an element of Rn such that AX equals to 0, such that AX equals to 0. Null space is actually the solution, which is X, which is an element of Rn such that AX equals to 0. AX equals to 0. Okay, theorem 2.3. 2.3, and this is a theorem. If A is an M by N matrix, then the null space of A is a subspace of R. Is a subspace of R. It's a subspace of R. So you need to remember this. So the column space is a subspace of the row of Rm, and this one is a subspace of the column. For example, this one is example number 5. Let's A be an or be a 4 by 5 matrix. Give integers P and Q such that the null of A is a subspace of Rp, and the column space of A is a subspace of Rq. So what are P and Q? So from there, solution. So we know that the null space of A is a subspace of what? R what? Rn, right? And Rn are the number of what? Whereby n are the number of columns. And the number of columns here are what? 5. And this one is equals to 5. So this is equals to 1. P. So that is equals to P. And the column space of the column of A is a subspace of Rm, whereby M is equals to Q, and this Q is the number of what? Number of rows. And this is equals to 4. Is equals to 4. Any question after that? Okay. Another example number 6. Determine, or let A be equals to -3, -2, 0, 0, 2, -6, 6, 3, and 3, and U equals to 1, 14, and -9. Number A, determine whether U is in null of A. Determine whether U is in null of A. So how do we get this? How do we get this? So what we do here is we know that the null space of A is the same as U, right? Whereby A of U is equals to what? Is equals to, it's the same as, wait, it's equals to U. And this U is an element of what? R. In our case, this is R3, right? R3, whereby A of U is equals to what? Is equals to 0. So what we need to do is we need to check whether A of U, A multiplied by U, is equals to 0 vector. So in this case, we want to check whether -3, -2, 0, 0, 2, -6, and 6, 3, 3 multiplied by 1, 14, and -1, 9 is actually equals to 0. So when you multiply that, so let's check the first one. -3 multiplied by 1 is -3, -2, and this one is -28. Of course, it will not be equals to what? 0. It is not equals to 0, right? So the first entry there is not equals to 0. It is equals to -30. The next one is 0. The next one is 28, and then the next one is 54, right? And the next one is actually 82. The next one is 6, that one, and this is equals to 21. And this is not equals to 0, 0, 0. So it is not equals to 0, 0, 0. So then, so U is not in null space of A of R3. It's not in the null space. Number B. Describe the subspace null space of A of R3. Describe the subspace. Null space A of R3. So what do we need to do here? What do we need to do here? So here we need to get now the solution. So here we need to get the null space of A, which is equals to X. And this X is actually element of R3 such that AX equals to 0. So we need to get the solution, which is X. Then in this case, then our AX equals to 0. So we have this here. So we want to get a solution of AX equals to 0. So then we write the augmented matrix here, which is -3, -2, 0, 0, 2, -6, 6, 3, 3, and then 0, 0, 0. And then you do what? We reduce it completely. We reduce it completely. So I already solved these. So when you reduce completely, reduce completely, then what you should get is 1, 0, 2, 0, 0, 1, -3, 0, then 0, 0, 0, and 0. So what? That is what you're supposed to get. The reduced echelon form. You want us to reduce it, or you're good with it? So when you go home and reduce that, that is what you should get. Now, here, the basic variables are x1 and x2. Free variable is equals to x3. x3. Then our new equation here is x1 plus 2x3 equals to 0, and x2 minus 3x3 equals to 0. Then x1 equals to minus 2x3, x2 equals to 3x3. Then our solution set here is our x will now be equals to x1, x2, x3. And this is equals to x1 is minus 2x3, 3x3, and then our free variable x3. And this is equals to x3. And this is equals to minus 2, 3, and 1. 2, 3, and so then our null space here, actually for any x3. So the null space of A is equals to x3, whereby this is minus 2, 3, and 1, such that x3 is an actual element of real number. And this is the same as the span of -3, 2, and 1. -2, 3, and 1. So you can have to show this. Oh. Any question up to that? So the solution of the null space of A is actually the solution AX equals. Yeah, the vectors which are formed from that is the null space of A. Okay, now let's look at the next section, and this is the basis of a subspace. The basis of the vector space. Let's start by writing the definition. If we let H be a non-zero subspace of Rn, and we already saw this one in our introduction. We say that H is a subspace, it's a small space in the whole vector space. Then a basis for H is a subset, which we can name this one as a beta B of H, such that number one, the vectors in B are linearly independent. And then number two, B spans H, I in H is expressible as a linear combination of the vectors in B. So the basis of H is the subset of B of H such that the two here are satisfied. So B is linearly dependent and also B spans H. B spans H. For example number 7. Show that the standard vectors E1 all the way to En is a basis for Rn. Is a basis for Rn. So actually, without even solving this, so we cannot, of course, see that this is a basis for Rn because these are standard vectors, so it's 1, 0, 0, like that up to the last one. So all the rows and columns have the pivot positions. So actually, they are what? Linearly independent. And then, of course, they span Rn. So let's see the proof here. Then we note that when we put this one in a matrix form, then E1, E2, all the way to En is actually the what? The identity matrix. It's actually the identity matrix. Then that is the identity matrix. Then number one, the n by n matrix In has n pivot positions. So linearly independent. So it is linearly independent. Number two, every row of In has a pivot position. So E1 all the way to En spans Rn. Or every row of In has a pivot position. So this vectors here spans Rn. Example number 8. Show that B1, B2, and B3 is a basis for R3, where B1 equals to 1, 0, 0, B2 equals to 1, 1, 0, and then B3 equals to 1, 1, 1.
So without even solving this, you can actually see that when you put this one in a matrix form, then all the rows that have the pivot position.
So the solution, without even solving it, we can see that number one, the 3 by 3 matrix, which is B1, B2, B3, has 3 pivot positions. Hence, linearly independent. Number two, every row of this matrix of matrix B1, B2, B3, every row has a pivot position. Hence, the matrix B1, B2, B3 spans what? Spans R3, spans R3. Okay, another example number 9, which I know I'll give you something similar to this in your exam. Example. Display an echelon of a matrix A. So this example number 9 is just displaying the matrix, the echelon form of the matrix A. Now find a basis for column space of A and a basis for null space of A, whereby we have our A to be equals to 3, -1, 7, 3, and 9, -2, 2, -2, 7, and 5, -5, 9, 3, 3, and 4, and then -2, 6, 6, 3, and 7. And this will give us, when you reduce this to echelon form 3, -1, 7, 0, and 6, 0, 2, 4, 0, and 3, 0, 0, 0, 1, and 1, 0, 0, 0, 0, and 0.
So these are as we produce echelon form.
Now, what are the bases for the column space of A? What are the bases for the column space of A and also the null space of A? So let's start by, we can name this one as A1, A2, A3, A4, and A5. A5. We can name them. Now, number one. Okay, now if you look at this H reduce the echelon from here, then we have the pivot position on the first, second, third, fourth, fifth. So we have now since first, second, and fourth columns of A are the pivot positions or the pivot columns. So they have the pivot columns there. Then the vectors, which are A1 equals to 3, -2, -5, and -2. Our A2, which is equals to -1, 2, 9, and 6, and our A4, which is equals to 3, 7, 3, and 3, are linearly independent. Since the three
of them, this one, this, and actually, yeah. So the three columns have the pivot positions. So if we bring the three columns together, then it will actually be having the pivot position here, the pivot position here, the pivot position here. So the three of them have the pivot position. Then if the three of them have the pivot position, they are what? Independent.
So they are linearly independent. Okay. Now, then, if B is an element of the column space of A, if B is an element of the column space of A, then AX should be equals to 0. AX should be equals to B is what? Is consistent. AX equals to B is consistent.
So we remember the definition of column space.
So then our A and B is now equals to our AB is now equals to bringing our A there, which has been reduced, which is all this, okay, which is 3, 0, 0, 0, and then -1, 2, 0, 0, and then 7, 4, 0, 0, and then 0, 0, 1, 0, and 6, 3, 1, 0 there. And then now our B, which maybe has been reduced, can be the star there, star there, star there, and of course 0.
So we take out B. And we can do it as B1, B2.
So we can actually put there, since it has been reduced. So we can actually, it changes. It's not like B1, B2 again. So you can just put the star, the star, the star, which has been reduced. Then this is now the same as A1, A2, A4, and now our B. is now similar to now taking now our 3, 0, 0, 0, -1, 2, 0, 0. And then we have the fourth one, which is 0, 0, 1, 0, and then star, 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 and 0. Okay, so taking now the ones which have the pivot positions. So these, this, one, and now the last, which is now, therefore, since A1, A2, A4, and B, since the matrix, that one, the middle matrix, and then is consistent, since that one is consistent, then we get B to be the element of the span A1, A2, and 1, and A4, A1, A2, and A4. So then we get column of A to be equals to the span of A1, A2, and A4. And so it will now be 3, -2, -5, and -2. And then the next one is the one for A2 is 1, 2, 9, and 6. And then the one for A4 is 3, 7, 3, and 3. And this is actually is a basis for column space of basis for the column space of A. Okay. Now, so basically I was trying to explain to you how the basis of the column space of A is coming by. You don't have to write this one. So what you need to do is when you ask a question like this, then basically to find the basis for the column space of A is first of all, you reduce the matrix A. So once you reduce the matrix A, you get this one. So note that it is actually, you reduce this one to echelon form, not the reduced echelon form, to echelon form. So the columns which have the pivot positions are actually the basis for what? For the column space of A. So once you reduce and you find those columns with the pivot position or the pivot columns, then this column here will now be the what? The basis for the column space. So you don't have to write all this. So you just write. Okay. Yep. Okay, now what about the null space of A? So what about the null space of A? This one is number 2. So the null space of A is the solution set of AX equals to what? Equals to 0. So the null space of A is the solution X equals to 0. So in this case, then we already have our reduced one, which is here. Then what we need to do is we now add the what? 0, 0, 0. And then we do what? We reduce it completely to get the solution. So we have 3, 0, 0, 0, negative 1, 2, 0, 0, 7, 4, 0, 0, 0, 0, 1, 0, and then 6, 3, 1, 0. And then we now add what? 0, 0, 0, 0. And then we reduce it completely. And we reduce it completely to reduce echelon form. Now, once we reduce this, then reduced echelon form, then what you should get is 1, 0, 3, 0, 5 over 2, 0, 0, 1, 2, 0, 3 over 2, 0, 0, 0, 0, 1, 1, 0, and then finally 0, 0, 0, 0, 0. So that is our reduced echelon form. So then our basic variable is x1, x2, and what? x4. Our free variable is x3 and what? x5 and x5. x5. Then our solution, our new linear equation here will now be x1 plus 3x3 plus 5 over 2 x5 equals to 0. x2 plus 2x3 plus 3 over 2 x5 equals to 0. Then x4 equal plus x5 equals to 0. So then x1 here equals to minus 3x3 minus 5 over 2 x5. x2 here will be equals to 2x3, which is minus 3 over 2 x5. Then x4 equals to minus x5. So then our solution set, solutions sets of AX equals to 0 is our X, which is equals to x1, x2, x3, x4, x5. And this is equals to minus 3x3 minus 5 over 2 x5. x2 is minus 2x3 minus 3 over 2 x5. x3 is our free variable. x4 is minus x5, and then x5 is what? Free variable, which is x5. So then this is equals to x3, which is the same as minus 3 minus 2, 1, 0, and 0, plus x5, which is equals to minus 5 over 2 minus 3 over 2 x5 there is 0, x5 there is -1, x5 there is 1. For what? For any x3 and x5. For any x3 and x5. So then the null space of A is equals to x3, which is -3, -2, 1, 0, 0, plus x5, which is equals to -5/2, -3/2, 0, -1, and 1, such that x3 and x5 are elements of real number, which is the same as the span of what? -3, -2, 1, 0, 0, and what? 5/2, 3/2, which is minus 0, -1, and 1. So therefore, -3, -2, 1, 0, 0, -5/2, -3/2, 0, -1, 1 is a basis for null space of A. It's a basis for null space of A. Remark. If A is an M by N matrix, then the sets all pivot columns of A form a basis for column space. So this is what I just said. A is M by N matrix. All pivot columns of A forms a basis for the column space of A. Okay, that is the end of section 2.8. Now let's come to the next section. This is 2.9. And this one is dimension and rank. The dimension and rank. So this is a small section, it's not that big. So we will start by looking at the coordinate system for the subspace of the vector space Rn. Coordinate system. Okay, so let's write this theorem, which I will not prove. You will look at it from your textbook. If we let H be a subspace of Rn and our B equals to, let's say, B1 all the way to B, let's say, BP. B an ordered basis for H. Then every vector V, every vector V of H is uniquely expressible as V equals to C1 B1 plus C2 B2 plus CP BP, where C1 C2 all the way to CP is an element of real number.
So if we have, so this B is actually the linear combination of the product basis.
Then this will lead us to this definition here, definition 1.2, whereby if we let H be a subspace of Rn and B be the ordered basis, which is B1 all the way to, let's say, BP. Be an ordered basis for H given a vector V of H, which we just write the way we've just written up there, V to be equals to C1 B1 plus all the way to CP V BP, where C1, C2, all the way to CP is an element of real number, and define the B coordinate vector of V to be V, and then we put here B to be equals to the solution, which is C1, C2, all the way to CP, which is a vector in R, which is a vector in R. So the B coordinates,
we have this as B is a linear combination of the ordered basis here. Then the B coordinate, which you usually write as V and the B down here, is actually the solution that you get. So you solve this with C2 and
CP. For example, example number 1. Let's B be equals to E1, E2, all the way to, let's say, En. Be the standard basis for Rn. And X be equals to X1 all the way to Xn. which is element of Rn. Find the B coordinate vector of B. Find the B coordinate vector of B. So how do you get that? So in this case, then V solution. So we know that since x equals to x1 e1 plus x2 e2 plus xn en. So that is what we then our x b there is actually the solution, which is what? It's actually x1, x2, all the way to what? Xn. This is the same as what? X. So if you solve this, then what you get here, since these are the standard basis there, then because they're linear independent, they're just 1, 1, 1. X1 is actually this X1 is and solutions, yeah, which are the same as the vector X, the vector X. Example number 2. Show that V is in the subspace H of R3 with ordered basis B, which is equals to B1 and B2, where B1 equals to 1, 1, 0, B2 equals to 1, 0, 1, and B equals to -2, 1, -3. Find the B coordinate vector of V. Find the B coordinate vector of B. Okay, so the first one, solution. So in this case, we just want to show that x1 b1 plus x2 b2 is equals to what? Is equals to. So that is what we want to show. So we already have b1, b2. Then to show that this is actually equals to b, then we need to put that one in aggregated matrix form, and then we reduce to see whether that one is what? Consistent. So we want to see whether this is consistent. So when we put this one in augmented matrix form, then we have 1, 1, 0, 1, 0, 1. And then for the V is -2, 1, and -3. And then we do what? We reduce to H form. And when we reduce this, then we get 1, 1, -2, 0, -1, 3, and then 0, 0, 0. And since the third row there is not contradictory, then it is what? Consistent. So it's consistent. So therefore, so x1 b1 plus x2 b2 equals to b is consistent. is consistent. So that is the first section. Now let's find the B coordinate vector of V. That means we want to get a solution x1 and x2. So then we do what? We reduce that completely. So we have echelon form here, then we reduce it completely. So this is 1, this is 2. So we have 1, 1, -2, 0, -1, 3, 0, 0, 0. We reduce this completely. That means we are making this 0, then you add 1. There will be R1 plus R2. And what we get there is 1, 0, and 1, 1. Then we make this one to be 1. And then R3, R2, we make this by multiplying by -1, R3. And this is 0, 1, and 1, -3, right? And then 0, 0, 0. So that is what we get. So therefore, x1 is equals to what? 1, and x2 is equals to -3. x2 is equals to 3. So therefore, our B is equals to what? 1 and -1 and -3. 1, -3. So that is our B coordinates. So then B is equals to, since x1 is 1, and then B1 minus 3B2. So that is like that. Example number 3. If we let B to be equals to B1, B2, and B3, be an ordered basis for subspace H for R3, where B1 equals to 2, 0, 3, and B2. Actually, this is B1 and B2. B1 and B2. And B2 equals to -1, 1, and 2. If V is a vector in H and the B coordinate, which is B, is equals to 1 and -2, then find So if you're given the B coordinates and then you're also given the solution is equal, then let's find. So it is simple. So the solution, you just get what? So we know that B is equals to x1 B1 plus x2 B2. We already have x1, which is 1, x2, which is -2. We have B1 and we have B2. Then this is the same as x1, which is 1. And then we multiply by what? 2, 0, 3 minus for this 2. And then what? 1, -1, 1, and 2. And what we should get there is 4, -2, and -1. And that is solution. is the solution. Okay, so when we meet tomorrow, then we will look at the dimension of a subspace and rank of a matrix. So rank is just the number of bases in the column space and the null space. Like previously, if you look at these, if you look at what we just saw here. If you look at what we just saw here. So what are the number of bases here? There are 3. What are the number of bases here? 2. So the dimension of the column space here are what? 3. The dimension of 3. The dimension here are what? 2. The rank is the number, is actually the dimension of the column space. The rank is the dimension of the column space. That is so easy. So we'll just come and repeat the same thing, but what we're just looking for are this one, and then this, and then this, the dimension of the column space, which is the rank. Okay, I'll see you on tomorrow.